The LCM and HCF are two different important factors of mathematics while solving many of the problems, and we have discussed about LCM and HCF in the lower classes. So let's come as a recap to discuss about what is LCM and HCF in mathematics. So LCM, which stands for least common multiple, and HCF, which stands for highest common factor, are the two important aspects we are going to discuss today with examples. So here, if I take two numbers, let me start with LCM and HCF, the least common multiple and the highest common factor. So if I take two values, 12 and 18 are the two numbers I take, and I want to find the LCM of 12 and 18, and I want to find HCF of 12 and 18. So let's see how we are going to find for each of the answers and then differentiate between understanding the LCM and the HCF. So coming to this, let me start with 12, and using the prime factorization method, I should be able to find all the possible products in primes for 12. So as we know that 12, when taken in with prime factorization method, 2 times of 6, 2 times of 3, can be written as 2 square into 3 power 1, because 4 3s are 12 and there are two primes which are 2 and then 3, which can be written as 2 square times of 3. Therefore 12 can be written as 2 square times of 3 power 1, because these are the possible factors in prime, the prime factors for 12. Similarly, I find the prime factors for the other number in this example being 18. So when I want to find the product of primes for 18, again I try to find by prime factorization method the different possible factors, 2 9s, 3 3s and 3 1s, so that 18 can be written as 2 power 1 times 3 square, as can be seen from here. 2 into 3 into 3 can be written as 2 power 1 times 3 square. Now with these two, my LCM, if I wanted to find the LCM of 12 and 18, then I use the method where it says that LCM of 12 and 18 is nothing but the product of the greatest powers with common prime factors. Now LCM of two numbers is defined as the product of the greatest powers with common prime factors. This is how we understand LCM connected with prime factors. So let's see how we can simplify the LCM of 12 and 18 using this exclusive method of identifying the product, identifying the greatest powers with common prime factors and then multiplying them. So in this case of 12 and 18, I identify that the greatest power here is 2 power 2 and the greatest power here is 3 power 2. Therefore, for each of them, the product of the greatest powers with common prime factors. So here I find the common prime factors 2 squared and 3 squared. Therefore, the greatest powers here are this and this, which I'm going to multiply as 2 squared times 3 squared as the product using the statement out here. So in this case, I get this to be 2 squared, which is 4, and 3 squared, which is 9. 4 times 9 is 36. Therefore, LCM of 12 and 18 is said to be 36. So LCM of 12 and 18 is 36 by using this concept. The least common multiple of 12 and 18 is equal to 36. So coming to the next, if I wanted to find the HCF of 12 and 18, the highest common factor of 12 and 18, then also I have a formula similar to this LCM of two numbers. So when I wanted to find the HCF of 12 and 18, then this is identified as the product of the least powers, here being the greatest powers. I have here product of the least powers with common factors, with common prime factors. So when I identify the least powers here, clearly I identify that the least power here in case of 12 is 3 power 1 and the least power here is 2 power 1. Therefore, when I want to find the HCF of 12 and 18, I take the product of the least power 3 power 1 times the least power in case of 18 2 power 1, so that I get this times this, and this gives me the answer to be 3 times of 2, which is 6. Therefore, the highest common factor of 12 and 18 is 6, and the least common multiple of 12 and 18 is 36, is how I identify the difference between understanding of LCM and HCF. So similarly, there's a small note I would like to make here, that HCF is also called is sometimes referred as GCD, the greatest common divisor. The highest common factor is also referred sometimes as greatest common divisor, abbreviated as GCD. Next, one of the most important relation between LCM and GDC in understanding through the connection between LCM and GDC is that they are very much related through a mathematical equation, where if I wanted to find LCM and GDC of two numbers, say A and B, my numbers are A and B, then LCM into HCF is the product of the numbers. If I wanted to find LCM or HCF, I can also use this formula if provided I know one of them, either LCM or HCF, but they are two connected with LCM times HCF is equal to A times B. The LCM into HCF is product of the numbers, is how we understand the concept in this relation, and this is very important because this connects HCF and LCM in with a mathematical equation. So this can be verified using the previous example above here, where A and B are 12 and 18 respectively, and LCM is already found to be 36 and HCF is already found to be 6. So let's see if this verifies very much for any numbers, any two numbers A and B. Therefore, as I already found the LCM of two numbers 12 and 18 to be 36, then 36 times of the HCF, which is 6, must be equal to the product of the numbers, which is 12 times of 18. And as I clearly see that 36 multiplied with 6 is 216, and 12 8s are 56, 12 ones 12, 12 8s 96, 12 ones 216, which is clearly true. Therefore, this theorem, this formula holds true for any two numbers taken into consideration, and therefore this supports the statement. Now let's see how we can convert the given decimal into the rational form, that is P by Q form. We have already discussed about rational numbers as the numbers which can be expressed in the form of P by Q, where P and Q are integers and Q is not equal to 0. The definition has already been discussed in the previous session. So today we'll see how we can convert the any sort of decimal into the rational form, the P by Q form. So let's start with an example problem. So converting decimals to rational form. So let's take an example problem and see how a decimal number can be converted to its respective rational form, a rational number. For example, if I have 0.125 as the number, then this is clearly in the decimal place, is a decimal number with 3 values after the decimal. So 0.125 can be expressed in rational form by simply taking this with 125, whatever is there after the decimal, I just write down, and then because I have the decimal here, when I want to move the decimal 3 units to the right, I divide by 1000, as we have already discussed in the lower classes. Moving of the decimal to the right makes me divide with 10 each time you jump from 1, 2 and 3. So 3 steps out here, 1, 2 and 3. Therefore I get 10 power 3. If I need to move 5 steps to the right, then I write this as 10 power 5. So moving to the right would divide with 10 power n, and moving to the left would be multiplied with 10 power n. And therefore here I get this as 125 by 1000, which is a rational number because p by q form with p and q as integers and q is not equal to 0, q being 1000 out here. So this is how I convert the given decimal into rational form. But how do I give the most simplified answer for this? I wanted the most simplified answer for 125 divided by 1000. So in this case, when I want to further simplify, I clearly understand that I can divide this with 5, where I get this as 5 2s are 10, 5 5s, 5 200s, 5 5s, 5 40s, 5 1s, 5 8. Therefore, the most simplified answer for this is 1 over 8. So the rational number corresponding to the decimal 0.125 is said to be either 125 by 1000, or when simplified further, the most simplified answer being 1 over 8 is the answer for the given concept. So this is identified to be the rational number. So let's take another example which supports conversion from decimal to the rational number. Now this is the number which I wanted to convert to the rational form. So in this case, I just understand that I need to move my decimal 1, 2, 3, 4, 5. So it's a 5-step process to move this decimal to the right to make p as an integer. So therefore, when I have this 1, then because I move 5 steps to the right, I simply raise 10 to the power 5. And then I get this to be 1 over 1, 2, 3, 4, 5 is 1 lakh. 1 over 1 lakh is the rational value for the given decimal 0.00001. Yes. Now we have discussed about converting the decimal to the rational form. Also, we have to decide on what we conclude from seeing different answers. So definitely, I would like to take one more example to make a conclusion on the relation between the numerator and denominator of the rational numbers when converted from decimals onto their respective rational form. So when I take 53.25 and then if I take 53.24 and I convert this into the rational form, then because the decimal has to move 2 steps to the right, I understand this as 5324 by 10 square, which is 100, and this on further simplification gives me 250s, 2 2s are 4, 13, 2 6, 2 6, 2 2s, 25. So 1331 by 25 is the most simplified answer for the given decimal. So as I see in each of the cases, there should be some conclusion which I need to make between the relation between the numerator and the denominator. So using the different examples, I make the following conclusion which acts as a theorem. So if any decimal value which terminates, because in every case I have taken those values and decimal values which terminate, they have some ending out there. So the limited decimal value, if any decimal value terminates, then its rational form, then it can be expressed in rational form P by Q, and not only that, and also its prime rational form, and also its most simplified answer will be, and its P and Q will be coprimes. Now coprimes are those values which are considered to be when the GCD of those two numbers is 1. So when do I say that two numbers are coprime? If I say that two values are coprime, then the GCD or HCF of those two numbers must be 1. Then that implies the two numbers are coprime. So this is the testing for the coprimes. So when I want to test for two numbers to be coprimes, I just find the HCF of those two numbers, and if I get the HCF to be 1, the HCF which is already discussed in the previous session, if the HCF of two numbers is 1, then the two numbers are said to be coprimes to each other. So my statement here says that if any decimal value terminates with limited decimal values, then it can be rational, it can be expressed in rational form P by Q, and also its P and Q will be coprimes. And further, Q can be expressed in the form 2 power n 5 power m, where n and m are non-negative integers. So this is how I conclude the theorem, but the whole of this concept is what we need to understand and very important. So why did I say that Q can be expressed in the form 2 power n and 5 power m? What is the need? Because whenever I wanted to convert the decimal value into the rational form, I have taken divided by 10 power, 10 power, 10 power, which is 100 as 10 square. So whenever a decimal value is converted into the rational form, the concept here comes that if the decimal terminates, then I divide with 10 power the number of steps where the decimal has to jump to the right. So this 10 power clearly makes me understand that since 10 has the prime factors 2 and 5, therefore each of 10 power n will have its decimal 2 power. If I have 10 power k, then this 10 power k can be written as 2 power n into 5 power m. So 2 power n into 5 power m is how I can express 10 power k. So as can be clearly seen in case of 10 being with factors 2 and 5. So that's the reason I get here Q always being in the form 2 power n and 5 power m, the product of factors. As I can see here, 1 by 8 can be written as 1 by 2 power 3. So here n is 3, m is 0 in case of this. This can be written as 1331 by 25. I can write it as 5 square, which is 5 power m. M is 2 and n is 0 because there's no 2 power term. So everywhere I see the same concept. Similarly, this can be written as 1 by 10 power 5, that is 2 power 5 into 5 power 5, and then m is 5 and n is 5. So every terminating decimal value which is expressed in its most simplified answer in rational form will have its denominator in the form 2 power n into 5 power m, where n and m are non-negative integers, is how I conclude the theorem. This is the theorem which supports with the examples considered here.